Good morning, everybody. Today we will study some results on connectivity of graphs. And the first result is some bound on the edges. It is clearly understood that the graph would be connected if there are more edges. And that is the theorem that we get here, that any connected graph with n vertices has at least n minus 1 edges. The result is only the necessary condition, that is, it is not true that every graph with n vertices and n minus 1 edges are connected. Whenever we have less than n minus 1 edges for n vertices graph, and that must be disconnected. The proof is very simple, and it is induction on the number of vertices n. So if we have the basic step, if we have that n equals to 1, that is a single vertex graph and there is no edge, and therefore 1 minus 1 is 0. So the graph has at least 0 edge. And that gives us the basic step. And then as an inductive hypothesis, we assume that suppose n is greater than or equal to 1, and suppose any connected graph with n vertices has at least n minus 1 edges. And the induction, we start with a graph with n plus 1 vertices. Now first we note that if the degree of any vertex is greater than or equal to 2, in that case the case is very simple. Now you must note that the graph is a connected graph, and we have taken that n greater than or equal to 1, so n plus 1 must be strictly greater than 1. So the graph has at least 2 vertices. And since the graph is connected, so there is at least one edge here. Now, if degree of each vertex is greater than or equal to 2, then the total sum of degrees of vertices is naturally greater than or equal to 2 times n plus 1. And that is strictly greater than 2n. And so you have that the graph has number of edges greater than n. So it has at least n edges that is required, and it is more than it is greater than n. Now suppose we consider the graph as a vertex of degree 1. Now what we do, that we just delete the vertex of degree 1, and since it is a degree 1 vertex, if we delete it, only one edge is deleted. And since only one edge is deleted and one vertex is deleted, now the new graph has n vertices, and then by induction hypothesis we have there are at least n minus 1 edges, and that with the edge deleted will give us in the original graph at least n edges. And so this completes the induction, and the result is proof that every n vertex graph has at least, n vertex connected graph has at least n minus 1 edges. So if you just revise the proof of the theorem, you see that we want to prove that any connected graph with n vertices has at least n minus 1 edges. And we start with the induction on the number of vertices n. The proof starts with the basic step for n equals to 1, and we see that it is a single vertex graph. So if there are loops, then we have more edges, but if there is no loop even, then there is no edge, and you have at least 0 edge. That means 1 minus 1 is 0, and so it says that the result is true for n equal to 1. For one vertex connected graph, there is at least 0 edge. And then we start with induction with the inductive hypothesis that suppose the result is true for all the n vertex connected graph that has at least n minus 1 edges. So we first note that since the basic step is completed with n equal to 1, now we have considered n is greater than or equal to 1. N plus 1 is greater than 1, and so there are at least 2 vertices. Since it is a connected graph, so there cannot be any vertex of degree 0. So all the vertex of degree greater than equal to 1, and so we first consider the case if all the vertices are of degree greater than equal to 2, then you know that the sum of degrees of vertices greater than equal to twice n plus 1, and that is greater than 2n. So the number of edges, which is half of the sum of degrees of vertices, is greater than n, and that is more than we require. That is, we require that it is greater than equal to n. Now we get, in this case, it is strictly greater than n. Now for the second case, we consider the graph has a vertex degree 1. So if the graph has a degree 1 vertex, we just delete it, and then we get a graph. And it is important to note that this graph must be connected, because it is only a 1 degree vertex. If we delete a 1 degree vertex, then only the vertex and the edge associated with it is deleted, and the rest of the graph remains to be connected, since the original graph was connected. And so we can use the induction hypothesis, and then we say that now it is an n vertex graph, a connected graph, and so it has at least n minus 1 edges. And now you just join this vertex and edge that we have deleted, and then you get that number of vertices increased to n plus 1, and the number of edges is at least n. So in the deleted graph, the number of edges was at least n minus 1. Now with the edge deleted, now it is greater than equal to n. And that completes the induction and the proof. Now these are necessary condition. However, one can understand, suppose we have a 10 vertex graph. So if we have any number of edge between 0 to 8, then the graph must be disconnected. So the graph, any 10 vertex connected graph must have at least 9 edges. So on the other way, if the number of edges is very low, that is, it is less than n minus 1, then we can understand the graph is disconnected. The next result is a sufficient condition, and this sufficient condition is that if the number of degrees of vertices is sufficiently large, then we have the graph is connected. And the theorem is that, suppose it is a simple graph with at most 2n vertices, and if the degree of each vertex is at least n, then the graph is connected. That is, if the degree of each vertex is greater than equal to half of the number of vertices, and then the graph must be connected. So it is a sufficient condition, and we prove in this way. It is also a very simple proof. We just prove in this way that suppose the graph is not connected, and then we will arrive at a contradiction that if the graph is not connected, so there are at least 2 components. So suppose you consider there are components g1, g2, gm, where m is greater than equal to 2. Now the degrees of vertex is each vertex is at least n. So since the degree of each vertex is at least n, and the graph is simple, so there are no parallel edges, no loops, and since the degree of a vertex is at least n, so in any component, if we consider a vertex, it has at least n other neighbors, and so each component contain at least n plus 1 vertices. So it is very simple to understand that if we take a component, we take a vertex, since the degree of each vertex is at least n, the graph is simple, so there is no question of loops and parallel edges, and so there must be n other neighbors of that vertex, and in that component at least number of vertices is n plus 1. Now we have assumed that there are m components, so number of vertices in whole graph will be at least m times n plus 1, and m is greater than equal to 2, so it is 2 times n plus 1, that is greater than 2n, and so it leads to a contradiction. So what we have assumed that the graph is not connected, that is not true, and so the graph becomes connected. So a very important application that you can get for this simple result, that suppose you want to make some bus routes in a country, and suppose there are 100 small towns in a country, and you want to make the bus routes in such a way so that from one town to another town one can go by changing a bus if it is possible. And then if one asks that how many direct route buses to be incorporated here so that one can travel from one town to another by, if possible, changing of buses. And then what you required, you require a network of this bus route that is nothing but connected. So you want the whole system is connected, and then the theorem says that if there are 100 towns, that is if there are 100 vertices, and then you have to just make the degree of each vertex is at least half of them. So if you run just 50 direct buses from each towns, the graph becomes automatically connected. So you see that a simple result give you a very good application, and that application you can make for some wiring of telephone exchanges also. Suppose there are 100 telephone exchanges in a city, and then you want to connect them through wiring, and you don't have to think that from which exchange you have to make the wire connection to the other. You just make for every exchange just half of that, that is 50 other exchange direct connection, and the whole graph becomes connected. So in this way you can have some application of this simple result. Now we can develop this result by a little bit in the way that we do not exactly the degree half of the number of vertices, or if you make the degree of each vertex is greater than equal to n minus 1 by 2, then also the graph is connected. That is, in the previous theorem we got that if there are at most 2n vertices and degree of each vertex is greater than equal to n, and then the graph is connected. Now this theorem says that if a simple graph has n vertices and then the degree of each vertex, if it is greater than equal to n minus 1 by 2, then the whole graph is connected. And this proof is very interesting proof. It basically uses some elements of simple set theory. Now we start, suppose, with a vertex V, and we consider that how many neighbors of this vertex V, and according to our condition that each vertex at degree greater than equal to n minus 1 by 2, and again the graph is simple. So the graph has at least n minus 1 by 2 neighbors. So the neighbor set, the cardinality of the neighbor set must be greater than equal to n minus 1 by 2. And since the graph is simple, it has no loops, and so the vertex V is not belonging to its neighbor set. Now suppose you are considering two distinct vertices U and V, and we want to show that either U and V are adjacent or U or V are adjacent to a common vertex, and then there is a path from U to V and the whole graph becomes connected. So we start with two distinct vertices, and if U and V are adjacent we have nothing to do, then they are joined by a path. But if they are not adjacent, then we notice that in the neighborhood set of U and V, neither U nor V is belonging to in their neighborhood set, because U is not belonging to the neighborhood set of U, and since V is not adjacent to U, so it is also not belonging to the neighborhood set of U, and the same holds for the neighborhood set of V. So U and V are not belonging to the neighborhood set of U and the neighborhood set of V. Therefore, they are not belonging to the union of these neighborhood sets. And so the union of their neighborhood sets has the cardinality at most n minus 2. But you see that neighborhood set of U and neighborhood set of V, separately has the cardinality at least n minus 1 by 2. Now we are just applying a very simple set theoretic result. You know that union of two set, the cardinality of the union of two set is equal to the cardinality of each set added with, and then take the difference, the intersection of these sets. So from this equation you get that each set has the cardinality n minus greater than equal to n minus 1 by 2, and the union has the cardinality at least n minus 2, and that is with the minus sign. And therefore if you just calculate this simple arithmetic, and you get that intersection is greater than equal to 1, and that gives you there must be a common neighbor of u and v. So u2, and suppose the common neighbor is w, so you have an edge from u to w, and you have an edge from w to v, so you have a path from u to v. And in this way you can join any two vertices of the graph by a path, and so by definition the graph becomes connected. So you see that this result says us that in a simple graph of n vertices, even if the degree is not greater than equal to n by 2, it is greater than equal to n minus 1 by 2, then also the graph becomes connected. And we prove in this way, just considering the neighborhood sets. I am just repeating the proof that if we take any two vertices u and v, the graph is simple, so the vertices are not belonging to their own neighborhood set. And if we want to show that these two vertices are joined by some path, so if u and v are adjacent, we have nothing to do. If they are not adjacent, we want to show that there is a common vertex of their neighborhood set, so that they can be joined by a path through that vertex. Now we notice that since they are not adjacent to each other and the graph is simple, so they are not belonging to their own neighborhood set, and so these two vertices are not belonging to the union of their neighborhood set. And then by simple this set equation argument, we can show that the intersection is at least 1. So there exists a common vertex of their neighborhood sets, and so through this vertex we can have a path between them, and the graph is connected. So we get three results here. The first was that for any connected graph with n vertex, there are at least n minus 1 edges, and this result says that actually this is a necessary condition, but it says that if the number of edges is less than number of vertices minus 1, then the graph becomes automatically disconnected. Then we have two sufficient results. One says that if the graph has at most 2n vertices and the degree of each vertex is at least n, then the graph is connected. And then, but in that case we consider it is a simple graph. And then there is another, a better result for simple graph of n vertices. If the degree of vertices is at least n minus 1 by 2, then also the graph is connected. So generalizing or just using these results, we can have another theorem that what happens for a graph with n vertex and k edge. So if the graph has n vertices and k edges, then we can say that the G has at least n minus k components. And here you see that if k is n minus 1, then you get that the graph has at least one component. That is, actually you get if the number of edges is less than n minus 1, so suppose it is n minus 2, then you get that the graph has n minus 2 components, that is 2 components, and so the graph becomes disconnected. So this result basically generalizing the result, that the first result we got that the n vertex graph with a connected graph has at least n minus 1 edges, and that is also a consequence of this general result. However, to prove this general result, we make the induction on the number of edges. Previously, we made the induction for the number of vertices. Now we want to make the induction with the number of edges. So suppose we start with the induction on number of edges k. Now if k equal to 0, then the graph has no edges, and so it is a null graph. So all the vertices are isolated, and so each vertex becomes a component of the graph, and so G has, the theorem says that G has n minus 0 components because k is 0, and so G has at least n components, and that prove the result that for k equal to 0, and that completes the basic step. Now we consider that suppose the result is true all n vertex graph and k edges where k is greater than equal to 0, right? Now we go for the induction. Now we prove the result by induction on the number of edges k. Now we start the proof with the basic step that k equal to 0. If k equal to 0, then the graph is a null graph and all vertices are isolated, and consequently every vertex becomes a component. And so if there are n vertices, the graph has n components, and n is n minus 0, that is n minus k here, and then the result is true that the graph has at least n minus k components. So the basic step is completed with k equal to 0, and so as an inductive hypothesis we consider the graph has any graph with n vertices and k edges, the result is true for k greater than equal to 0. Now we consider a graph with n vertices and k plus 1 edges, where k is greater than equal to 0. That means k plus 1 is greater than equal to 1. Now you consider an edge in G. Now if we delete just one edge from the graph G, and then the whole graph becomes of n vertices and k edges, and so by induction the number of components of the deleted graph, that is denoted here by G dash, is at least n minus k. Now if A is a parallel edge or a loop, then if we delete this, then the number of component is not changed. Then the whole graph and the deleted graph has the same number of components, and that is at least n minus k. That is more than we require, because we require n minus of k plus 1, that is n minus k minus 1 components at least to be here, and we got here there are at least n minus k components. So if the edge that we have deleted, that is a parallel edge or a loop, and then the number of components of the graph is not changed, and that is same as the original graph, and by induction hypothesis we have that number of components and deleted graph is at least n minus k, and that remains same for the original graph. Now suppose we consider that u and v the endpoints of the edge E that we have deleted, and suppose P is a path from U to V. Now the first case you consider that suppose the edge is not in the path, then the path is also in the deleted graph, because we have only deleted the edge E. So if there is a path P between the vertices U and V which is avoiding the edge E, and then we get that the graph becomes still having the same number of component. So as in the previous case, we have there are at least n minus k components, and that is more than n minus k minus 1. And so in this case also the result becomes true. Now suppose E is within the path P, and that means the path is nothing but UEV, because U and V are the endpoints of the edge E. So if E is in the path, then you can understand the path is nothing but UEV. And in this case, if we delete the edge E, then we get, if there is no other path between U and V, then this component where U and V were situated, and now this breaks into two components, and so we have one more component in the deleted graph than the original, and so the deleted graph has at least n minus k components. So the original graph has n minus k minus 1, that is n minus of k plus 1 number of components, and that is required for our result. So in this case also our result is true, and if the final case is that if there are other paths in the graph avoiding E that we have already discussed, that then there are n minus k components, and which is more than the requirement of n minus k minus 1 components. And so the induction completes and the proof is also completes. And so we just revise the proof. You see that we want to prove the result. Any graph of n vertices and k edges, the graph has at least n minus k components. And we prove by induction on the number of edges, that is k. The basic step we take for k equal to 0, and in that case the graph becomes the null graph. All vertices are isolated, so each vertex is a component. There are n vertices, and so there are n components, and n is n minus 0, and that proves that there are at least n minus k components. And for the induction, we assume that suppose the result is true for n and k, and then we want to prove for n and k plus 1. Now if there are k plus 1 edges in the graph, we just delete one edge, and to make the graph now with n vertices and k edges. Then by induction hypothesis we have at least n minus k components. Now we consider some cases. The first case is that suppose the edge we deleted, if it is a parallel edge or a loop, then the graph has same number of components, and so that it has at least n minus k components, and that is greater than equal to n minus of k plus 1 components. Now we consider that suppose u and v are the n vertices of the edge E, and if we have a path between u and v and which does not involve E, then they are also connected by deleting E, and so the number of components are not increased. It is still again n minus k, and that is greater than equal to n minus of k plus 1. And the final case is that suppose u and v are only joined by the edge E, and there is no other path between u and v, and in that case the u and v who are lying in some component that splits into two components, that component becomes disconnected now by deleting the edge E. So the deleted graph now have more than one component of the original graph, and so it is n minus k minus 1, and that is required basically n minus of k plus 1 completes the induction and the proof. So these are the four results that we got about the connectivity of graphs. So these are some relation between the number of vertices and edges, or in the terms of the degrees of the vertices, and also in the last result we got that there is some connection of calculating the number of components in terms of number of vertices and number of edges. So all these are bound type, and then we just concentrate with the concept of vertex connectivity of the graph. So now we just concentrate on this particular structure of the graph in relation with the connectivity, and we will see that how from a connected graph what are the properties of typically a vertex can have, so that the deletion of the vertices can make the graph disconnected. And the concept of cut vertex is arising from this understanding. If you look at the two graphs in this figure, then you see the vertex V3. If you delete the vertex V3 from this graph, and then you see the graph becomes disconnected. It has this part and the graph has this part. So the graph becomes disconnected by deleting the vertex V3. So this type of vertex we call a cut vertex. that is cutting or deleting the vertex, if that makes a connected graph disconnected, then we say that it is a cut vertex. In the graph G2, you see there is no cut vertex, because if you delete V1, then the graph is connected still. If you delete V2, then the graph is connected still. Similarly, if you delete V3, and then the graph is connected still. If you delete V4, then as in the V2, the graph is connected. And so there is no cut vertex in the graph G2. But in the graph G1, we have seen that V3 is a cut vertex. Now we go for the formal definition. Let G be a graph. A cut vertex is a vertex V if deletion of that vertex produces a subgraph G minus B such that the number of components of G minus B is more than the number of components of the graph G. So cut vertex we define more generally, not only for the connected graphs, we also can define more generally for disconnected graphs also, that is deletion of the vertex if increases number of components, then we say that the vertex is a cut vertex. So our natural question arises that which are the cut vertex if we can characterize the cut vertex, and that theorem exactly characterizes the cut vertex. In this result, we will characterize the cut vertex, and we see that the result says that if G is a connected graph and then V is a cut vertex, if and only if you will find two other vertices different from V, U and W, such that V is on every UW path in G. Now to prove the result, first we prove the direct part, that if we consider that V is a cut vertex, and now if we delete the vertex, since the graph was connected, now it becomes disconnected, because graph had one component as a connected graph. Now by definition of cut vertex, it has now more than one components. That means the graph becomes disconnected, and the number of component was 1 and now it is at least 2. So suppose you consider two components G1 and G2 of the deleted graph G minus V, and you choose the vertex U from G1 and the vertex W from G2, and then obviously U and W are different from V because they are in different component of the graph from which we have deleted the vertex V. Now you see that since the graph is a connected graph, that is the original graph was a connected graph, so there is at least one U to W path in G, and all the UW path in G are not present in the deleted graph, and therefore every UW path must pass through the vertex V. Otherwise you could have another path avoiding V from G1 to G2, that is from U to W, that is from the component G1 to G2, and the deleted graph would be connected, but the deleted graph is disconnected into two components G1 and G2, and so every UW path must pass through V, and so we get the direct part. Now the converse part is very easy. You see that then our assumption is that there is a vertex V for which there are two other vertices U and W in G, such that V is on every UW path. So we are assuming that there is a vertex V, there are two other vertices U and W, and V is lying on every UW path, and we want to prove that the vertex V is a cut vertex, that is deletion of that vertex will increase the number of component. So you assume that suppose two vertices U and W are in G, both different from V, and V is on every UW path, and then you see that if you delete the vertex, there would be no U to W path, and so U and W must be now in the different components. But before they were joined by a path in the same component, but now they are in the different component. So the number of components of the graph is increased by deletion of V, and that says that V is a cut vertex of G. So this characterizes the cut vertices. In simple word, that cut vertex is such a vertex where we can have two vertices other, so that every path between them are passing through V. Now if we consider the graph G1, and if we consider the vertices V2 and V6, and then you see that if we want to join V2 and V6 by a path, then every path from V2 to V6, you see this is another path from V2 to V6, and this is another path from V2 to V6. So whatever path you are choosing, you see that it is going through V3, and so V3 becomes a cut vertex of the graph. Now the concept of cut vertex can be generalized to a set of vertices as a vertex cut set. That is, if deletion of this set of vertices and disconnects a connected graph or make the number of components higher, and then we say that this is a cut set of vertices. Now there is a very important parameter of graph, and this parameter is the connectivity, or we say the vertex connectivity more precisely, that is denoted by kappa g, and kappa g or the connectivity is the minimum number of vertices in G whose deletion from G leaves either a disconnected graph or a graph with only one vertex. So the connectivity or the vertex connectivity is the minimum number of vertices by deleting which we can get the graph disconnected or remaining only one vertex. Now I explain this with some figure. Suppose you have a graph like this. Now you see that if we delete some vertex, suppose this one, then we are living with this edge. Now we delete this vertex, then we are living with some single vertex, and so you see that deletion of two vertices of the graph gives you a single vertex graph. So the connectivity of the graph is 2. Deletion of any one vertex from the graph is neither giving you a disconnected graph nor giving you a single vertex graph. You are getting here an edge with the endpoints 2, and so it's a connected graph, and so at least you have to remove two vertices to get a single vertex graph from here. Now another figure you notice. Now if we delete this vertex, clearly you are seeing this is a cut vertex. If we delete this vertex, the graph becomes disconnected into two components. So the number of component was 1, now it is 2. So by deleting only one vertex, you can make the connected graph disconnected, and so the vertex connectivity or connectivity of this or kappa g of this graph is 1. Here the kappa g is 2, and here the kappa g is 1. And in either case, if for any k which is less than equal to kappa g, and we say the graph is k connected, that is, this graph is 1 connected and this graph is 2 connected also, but this graph is only 1 connected. The left hand side graph is only 1 connected, it is not 2 connected, but the right hand side graph, this is 1 connected and also 2 connected. So any number which is less than equal to kappa g. If the number is k, then we can say the graph is k connected, and maximum of this k will give you the connectivity of the graph. Before going to the results, we wish to develop another important concept, that is the distance between 2 points in a graph. The distance between 2 points in a graph is very important concept, and this is a length of the shortest path. This is the length of the shortest path between two vertices, and here you have to understand that there might be more than one paths giving the length of the shortest path. For example, suppose you consider this graph, and if you search the distance from u to v, you see there is one path from this way, and you see there is another path of this way, both of the length 2. You see there are two paths, both of the length 2, and both of them giving you the shortest path between u and v, because there is no less than length of the path between a and v. There is no one length path between u and v, so the distance is here 2. But there may be more than one paths giving this distance. But what is very much interesting, that the distance function gives you a metric on the set of vertices. You see, it is very interesting to note that, like the Euclidean distance gives you a metric when we study topological spaces or metric spaces, and here also you see that this distance function of a graph gives you a metric because it satisfies the three conditions of the metric, that it is always non-negative, and the equality holds, that is, we consider that d of u and equal to 0 if u and v are the same points, and if u and v are the same points, and then you have that d of u is 0. And it is also symmetric because the shortest path from u to v is same as the shortest path from v to u, because here we are considering the undirected graphs, and therefore d of uv is equal to d of vu. And the triangle inequality is also obvious, because when you are traversing from u to v and then v to w, and then that must be greater than equal to the shortest path from u to w, because that I am again explaining with a diagram. Okay, you see that suppose this vertex is u, and from u you go to v, and from v you go to w, and then you see that there might be another path directly from u to w. So, and that path, since this path is from u to v and v to w, so this is one of the path from u to w, and since the distance is the length of the shortest path, so this is one of the path, so it is greater than equal to the length of the shortest path between u to w. It might be also the shortest path, but that is why it is greater than equal to, but it is one path from u to w, so that must be greater than equal to the shortest path from u to w. And in this way you see that the distance function gives you a metric here. However, from this distance function we develop another important concept, that is called the diameter of the graph of G, and that diameter of the graph of G is the maximum of distance between any pair of vertices of a graph. So if we collect every pair of vertices in the graph, calculate the distances between them, and then the maximum of the distances between them will be called the diameter of the graph. The diameter is a very important concept of the graph, that from which we can understand that how close is one vertex with respect to the other. If the diameter is high, then we see that there are long distance vertices are there in the graph. But if the diameter is low, for example, if we have a graph with diameter 2, then we know that for any two vertices, either they are adjacent or they have some common neighbors between them. That is, from one vertex to another, from U to V, either you are having an edge between them or you having a path UWV, because the diameter is 2, so the maximum length of the shortest path between them is 2, so there must be a common neighbor of them, so that you can reach from U to V in 2 steps, but that is through 2 edges UWV. So in this way, diameter becomes very important part of the graph. Now all these concepts are ready, and then we go for the results. Now, using the concept of the distance of the graph, we can have a result, an interesting result, that if you have a connected simple graph with n vertices, where n is at least 2, then G has at least 2 vertices which are not cut vertices. So all the vertices of a graph cannot be cut vertices, and so at least you can get 2 vertices which are not cut vertices. The proof of the result is simple, but it interestingly uses the concept of the distance. Actually, the proof is like this. That is, if we consider the diameter of the graph, that is, which is the maximum distance between two vertices U and V, and then suppose you consider that this is the maximum distance vertices U and V in the graph, that is, U and V are two vertices such that DUV is greater than equal to dxy for all xy belongs to V. Then we will show these endpoints of this diameter, they are not cut vertices. So suppose on the contrary, we consider that suppose V is a cut vertex, and then you see that if we delete V from the graph, and then since it is a cut vertex, so the graph now splits into two components. It was a connected graph. If we assume that V is a cut vertex, now it splits into two components. And so there exists another vertex W in a component in which U is not lying there. And so U and W are now belonging to the different components. And all these are happening due to the deletion of the vertex V. The graph was previously connected, but now the graph becomes disconnected. So we are considering that U and W are in two different components. So all the paths between U and W, are through V. But then what happens? You see that the distance of U and W now becomes strictly greater than the distance of U and V, because from V to W there is at least one edge, and so U to V there is at least one edge. The distance of U and W becomes now more than the distance of U and V, because there is no path avoiding V. There is no path between U and W avoiding V, because we are considering that by deleting V, U and W are being into different components. So if there would be a path avoiding V, then the graph would not be disconnected. And now that since the graph is disconnected and U and V are situating in the two different components, so there is no UW path avoiding V. So all the UW paths are through V, and so that gives you that DUV is not the highest between all the distances of vertices, because UW distance is becoming higher than UV, and that is a contradiction. And this contradiction says that uh, V is not a cut vertex. Exactly in the similar way, you can see that U is not a cut vertex. So we have that any graph with at least two vertices, any connected simple graph with at least two vertices, there are at least two vertices which are not cut vertices. So this gives you the result of cut vertices and the vertex connectivity. And now we go for another concept that is called the parallel concept, that is called the edge connectivity. And it is likewise the case of vertex connectivity. We are defining that an edge is a cut edge if the deletion of this edge increases the number of components of G. Then we call this edge as a cut edge or a bridge. And similarly, we can define the cut set of edges if the set of edges whose deletion makes the graph disconnected or makes the number of components more. And then we can say that this is a cut set of edges. But interesting is the cut edge, or why we are calling this a bridge. It is now clear from this graph. You see that in these graphs, if we delete the edge E3, then the graph becomes disconnected into two parts. So E3 is acting as a bridge between these two components when we delete the edge E. So it is a cut edge of the graph. Similarly, in this graph, you see that E2 is also a cut edge, because if we delete E2, then you get that it will be broken into two components. Similarly, E1 is another cut edge here, because if we delete E1, then you get a single vertex and the rest of the graph as another component. So these E1, E2, E3 are cut edges of the graph, but you notice that if we delete, suppose E5, then the graph remains to be connected and it is not disconnected. So E5 is not a cut edge. Similarly, if you delete E6, then the graph remains connected and so it is not a cut edge. And also if you delete E4, here, and then you see the graph remains to be connected, and so E4 is not a cut edge here. So these three edges, E4, E5, E6 are not cut edges, but E1, E2, E3 are cut edges. Now let us characterize the cut edges, and cut edge characterization is very simple, that it says that if the graph is connected and then E is a cut edge, if and only if it does not belong to any cycle in G. So if we go back to the diagram, then you see that E4, E5, E6 are part of some cycle, that is this cycle B5, B4, V6, they are making a 3 cycle, and you see that E4, E5, E6 are part of a cycle, and so they are not cut edges. But E1, E2, E3 are not part of any cycle, and so they are cut edges. So which are the exactly cut edges? The edges in a graph which are not a part of cycle, they are basically the cut edge. Now we prove this result, that if we consider, suppose E is a cut edge, and then by definition the G minus E graph, that is the deletion of E from the graph G, becomes disconnected because the original graph was connected. So the number of components here should be more than 1, and so the graph becomes disconnected. Now we want to show that E is not a part of any cycle. Now here it is shown in very details writing. The basic idea I am giving you, that is very simple, that if we delete the edge E from a graph and the graph becomes disconnected, so you have one component in this portion, one component in this portion, and you get two different components. Now if E is a part of a cycle, then you see that some vertex, this vertex, suppose the endpoints of E are U and V, then after deletion of E, now we are assuming these U and V are into different components. But if E were a part of a cycle, then you see that even after deletion of E, there is a path between U and V, and which contradicts that G minus E is disconnected because you are getting a path between these two components. And this proves that no cartridge can be a part of a cycle, because deletion of that cartridge splits the graph into two components. The graph was originally connected, so now it splits the graph into two components, and in one component is there one endpoint of E and another component is another endpoint of E. And but if E were a part of a circle, then there should be a path avoiding E between U and V, and that means that this component are connected by two vertices of these two components are connected by a path, and that is a contradiction, and therefore E cannot be a part of any cycle. So this proves the direct part. Now conversely, suppose you consider that E does not belong to any cycle, and we prove that E is a cartridge, and that we prove in this way, that suppose E does not belong to any cycle, and after also deletion of this edge, the graph remains to be connected. But if E is an edge, and suppose its endpoints are U and V, and after deletion of E, if it is the graph is not disconnected, so there must be a path between U and V which is not involving E, and that path with the edge E in the original graph forms a cycle. And so it is a contradiction because we have assumed the graph E is not a part of any cycle, but here we see that after deletion of E, if the graph has to remain to be connected, and then there should be a path from U to V avoiding E other than involving E, and then this part has no edge common with E. So in the original graph, clearly this forms a cycle with the edge E, and so that contradicts that E is not a part of a cycle, and that proves that if E is not a part of a cycle, that must be a cartridge or a bridge. And so we prove the result that in a connected graph, E is a cartridge if and only if it does not belong to any cycle G. Now this we prove for the connected graph. Now we can see easily by using this result, we generalize this result for any graph which may not be connected also. This idea is very simple because you see that even if it is not connected, then if we pick up an edge, that edge must be in some component, and that component is connected. So in that component, if we apply the above theorem, we see that E is a cartridge of that component if and only if it does not belong to any cycle of that component. But that component is a subgraph of the original graph. So if there is a cycle of that component containing E, then there is a cycle of in G also containing E in the original graph. So the result is true for in general for any graph, that E is a cartridge if and only if it does not belong to any cycle in G. Now we come to the edge connectivity of the graph, and that we denote by kappa dash G. That is another important parameter of the graph G. And as we have denoted vertex connectivity by kappa G, now we are denoting edge connectivity as kappa dash G of a graph, and that is the minimum number of edges in G whose deletion from G leaves either a disconnected graph or a null graph, that is a graph with no edge. So if a set of edges, if we delete from the graph, then the minimum number of edges that can be deleted from the graph to make it disconnected or make it a null graph, then we say that that is the edge connectivity. And like the vertex connectivity also, for the disconnected graph, kappa dash G is 0, because if the graph is already disconnected, you have to delete 0 number of edges to make it disconnected, so it is 0 trivially. Or if the graph is a null graph, and then also we say that kappa dash G is 0. That is, if it is of single vertex, then also we say that kappa dash G is 0. And kappa dash G is 1 if and only if G is a Cut edge. That is, if there exists a Cut edge, then the kappa dash G is 1, because like the cut vertex, if the graph has a cut vertex, then the vertex connectivity is 1. Similarly here also, if there is a cut edge, then the edge connectivity is 1. Now we will get a very beautiful result relating kappa G, kappa dash G and the minimum degree of vertices. This is another important parameter of the graph, that is the minimum degree of the vertices is denoted by delta G, and actually the maximum degree of the vertices is denoted by capital delta of G, and the minimum degree of vertices is denoted by small delta of G. Now we will have a very beautiful result connecting kappa, kappa dash and delta G. The result is that in a simple graph, kappa G is less than equal to kappa dash G is less than equal to delta G. So vertex connectivity is always less than that of edge connectivity, and edge connectivity is always less than that of number of minimum degrees of the vertex. But before proving the result, we just get an example to understand this. Now you notice the graph in the left, it has a cut vertex. So kappa is here 1. But you see there is no cut edge here, because just we have proved that an edge is a cut edge if and only if it is not a part of a cycle. But here you see that every edge in this graph is a part of a cycle, and so there does not exist any cut edge in the graph. But if we delete these two edges from the graph, and then the graph becomes disconnected, and then the vertex V2 becomes isolated from the graph, and so kappa dash is 2, the edge connectivity is 2. At least you have to remove 2 edges from the graph to make it disconnected. So kappa dash is 2, and you see that delta G, the minimum degree of the vertex, is also here equal to 2. And so you see that kappa is less than kappa dash, and that is less than equal to delta here. That we will now prove in general, but in this diagram you see the vertex connectivity is 1, the edge connectivity is 2, and the minimum degree of the vertex is also 2. The proof a bit lengthy here. So the first case we consider that if kappa dash is equal to 0, and then we have that graph is disconnected, all these are null graph, and that also says that kappa g is also 0, because then the graph is already disconnected, so you don't have to remove any vertex to make it disconnected. Or if the graph is null graph, so either it is a single vertex graph or it is disconnected, then also you do not require any vertex deletion to be 0. So this case is very obvious. So if kappa dash is 0, then you have that kappa is also 0. Now the important part is that when kappa dash is equal to 1, and then the original graph is a connected graph and it has a cartridge E. Now U and V, if we consider the endpoints of this edge, and then you can understand that if you remove any of the endpoint U or V, then the edge also be deleted and the graph becomes disconnected. So if kappa dash is equal to 1, then kappa is also equal to 1. Because if there is a cartridge, and then if you delete any endpoint of that cartridge, then also the graph becomes disconnected. And so when the edge connectivity is 1, then the vertex connectivity is also 1. It is actually, you can write it in a separate result also. It is very important result that existence of a cartridge always implies the existence of a cart vertex in the graph. Now the general case, we want to prove that suppose the kappa dash g is greater than equal to 2. Now this proof is very beautifully constructed. You see that what we will do. In this case, we consider that the kappa dash g is greater than equal to 2. That means you have to delete at least 2 edges to make the graph disconnected. Now what we will do, suppose we consider the edge connectivity is R. So basically what we will do, we will separate the last edge to be deleted to make the graph disconnected, and we consider that first R minus 1 edge is in one group and the rth edge in the other group. And actually you see that if we delete one by one these R minus edges to get a graph H, the graph H still remains to be connected, because we assume that the edge connectivity is R. So deletion of R minus 1 edges cannot make the graph disconnected. The graph is connected after deletion of these R minus 1 edges. But then what happens? Now ER becomes a cartridge. Now the last edge, according to our assumption, by deletion of E1 to ER makes the graph disconnected. So ER is a cartridge of the graph H. Okay. Now you consider, suppose U and V are the end vertices of ER, and we consider the UI and VI are the end vertices of EI. Now what we will construct, this construction is very nice, beautiful. You see that what we will do, we will delete also parallelly R minus 1 vertices from G. Which R minus 1 vertices? Which are the endpoints of this E1, E2 up to ER minus 1. But none of them are equal to U and V. You can easily understand, suppose this is the edge E and its endpoints are U and V. Now for any other edge, EI, if EI is completely different from E, that is not having a common vertex, then the both endpoints UI and VI are different from U and V. So I can choose any one of them that will be not the same with U and V. But even if EI is an edge that has a common vertex with E, then also I can choose another endpoint of this EI which is not common to E, and Wi for each ei is such an endpoint of ei which is not common to u and v. And also we can choose so that Wi are all distinct, but we can see later on that is not essential to make Wi distinct. However, you can easily choose Wi distinct because you are choosing some vertex which is not common to E, and then for E1 you are choosing suppose this one, and for E2 suppose you are choosing suppose E2 is another one, so you are choosing this vertex. If E2 is in this common, you are choosing this vertex. So in this way, so both the vertices cannot be common to some E1 and E2 because then it will form a parallel edge because the graph is simple, so there is no chance of having the parallel edges. So always you are getting one vertex that is different from U and V, and these vertices you can choose distinctly. But however, the most important part is that W is an endpoint of Pi and W is different from U and V. That is the most important part. And then what we are doing, we are forming a graph K by deleting these vertices W1, W2 up to WR minus 1. Then what happens? Now deletion to each Wi deletes Ei, and so ultimately by this process we have deleted all the E1 to ER minus 1. Now look at the graph H. Compare these two graphs H and K. H is obtained by deleting E1 to ER minus 1. K is a graph obtained by deleting W1 to WR minus 1, where each Wi is an endpoint of Pi. So already we have deleted E1 to ER minus 1. But in the process of vertex deletion, not only EI is deleted, there are other edges incident to in Wi, then those edges are also deleted. And therefore, the graph may be connected, may be disconnected. So if the graph K is disconnected, and then you see that kappa G is then less than equal to R minus 1, because kappa G is the least number of vertex, the deletion of which the graph makes disconnected. We have already deleted R minus 1 vertices. So if the resulting graph is disconnected, then the minimum number of vertex deletion required for disconnectedness is less than equal to R minus 1. And naturally R minus 1 is less than R, and that is less than kappa dash G. But then you notice that K contains always ER. That is very much important. K contains ER because carefully we have avoided choosing the vertex different from U and V. So U and V are not deleted, and this edge ER has the endpoints U and V. So they are not deleted, and therefore K contains ER. If K is a connected graph, and then K contains the cartridge ER. Already we have proved in the second case. Here there is a printing mistake. Actually it will be case 2. You can make the correction in the book you have. In the second case, we have proved that existence of a cartridge gives you the existence of a card vertex. So if K is connected, and if it then it has ER as the cartridge, so it must have a card vertex that is one of the endpoint of this ER, and then kappa of K must be equal to 1. So kappa dash of K is also here equal to 1. And so we have that kappa of G is R. Then we require it was a connected graph after deleting R minus 1 vertices. So after deleting another vertex, it becomes disconnected. So kappa dash G is R, and that is same as kappa G is R, and that is same as kappa dash G. And so we get that this equality holds in this case. And ultimately we prove, combining all the cases, that this ordering of kappa kappa dash, we prove that kappa dash is less than equal to delta, and that is very clear because since the minimum degree of vertices is delta, so if we delete all these k edges, so suppose there exists a vertex V with the degree delta, then if we delete all these edges and then the graph this point becomes isolated, and so the graph becomes disconnected. So by deleting this delta edges, we can make the graph disconnected. So kappa dash is the number of minimum of edge deletion requires for disconnectedness, so it must be less than that of delta. So this part is simple. Now we want to prove that kappa is less than equal to kappa dash, and that is the case of 0. It is very trivial because in this case of 0, the graph is either disconnected or a null graph. In both the cases, kappa g is equal to 0. And now interesting case is that kappa dash g is equal to 1. So g has a cartridge, and if g has a cartridge, then each of its endpoints are cut vertices, and so g has a cut vertex, and so vertex connectivity is equal to 1. Then the final case where the edge connectivity is greater than equal to 2, then what we do, we take, suppose edge connectivity is r, so we suppose these are the set of edges which have to be deleted to make the graph disconnected, and so we make it two parts, either taking from E1 to ER minus 1, and we separate the last edge ER, and then we form a graph by deletion of the edges E1 to ER minus 1 from the graph and forming H, and then we suppose consider that U and V are endpoints of ER. Then for each edge EI, we are choosing the endpoint in such a way such that it is distinct from U and V, and also they are distinct between themselves. And then we are deleting those vertices, and after deleting those vertices, naturally these edges will be deleted. And we remember that since we did not touch any endpoint of ER, so the graph now contains ER. So now two cases may arise. The graph may be disconnected. If the graph is disconnected, then kappa g is less than equal to r minus 1 because we have deleted r minus 1 and we got a disconnected graph. And so we got kappa g is less than r minus 1, less than equal to r minus 1, and that is less than r, that is kappa dash g. And the other case is that if the graph is connected, then we have that ER is the cut edge, because the last edge that we have deleted, we have to delete to make the graph disconnected, and so K is a connected graph, then K has a cut edge ER. And so as in the previous case, we can get that it has a cut vertex also, and so the connectivity, vertex connectivity is here also R, that is the same as the edge connectivity. So this gives a very beautiful result, and that connects the ordering of kappa g, kappa dash g, and delta. Now we will learn some results about the two connected graphs. You can remember a graph is two connected if it requires removal of at least two vertices to make it disconnected. So it is a connected graph, and not only that, it has no cut vertex. That is, removal of one vertex cannot make it disconnected. You need at least two vertices deletion to make it disconnected. The result says that if G is a simple graph with at least three vertices, then G is two connected if and only if for each pair of distinct vertices there are two internally disjoint UV paths. Now let me explain what is called by two internally disjoint UV path. That means you can see in this diagram that there are two paths connecting U and V where there are no common vertices other than U and V. That is, within the path there are no common internal vertices, and then we say that these are two internally disjoint UV paths. Now you can remember that the definition of a connected graph is that any two distinct vertices are connected by a path. Now it is generalization of this. Now it is a result that is on the analogy. Now it is the result that is you can get similarity of this result, that if a graph is connected, that means it is one connected, then any two distinct vertices are connected by a path. But here the characterization of two connected graphs says that if the graph is two connected, then every pair of distinct vertices are connected by two internally disjoint paths. And so we start with the proof. Now you will see that one part is very obvious. That is, suppose you consider that any pair of distinct vertices, there are two internally disjoint UV paths, then you can easily prove that the graph is two connected. The proof is as follows, that first of all, since they are connected by some path, so the graph is connected. Next, we want to show that there is no cut vertex. That is, deletion of one vertex cannot make the graph disconnected. Now, if there are cut vertex, you can remember the characterization of cut vertex says that there exists, if V is a cut vertex, then you know that there exist two other vertices U and W such that V is lying in every UW path. Now this cannot happen here, because whenever you are getting to vertices U and W, always you will get two internally disjoint paths, and V is an internal vertex between them, so V cannot be common to the two internally disjoint path. So the assumption that V is a cut vertex is false, so G has no cut vertex and the graph is two connected. So you see that this part is obvious. I am again showing by diagram. So you see that if you have two vertices U and V, and then since it is given that between any two distinct pair of vertices there are two internally disjoint paths, so at least you have one path, and so the graph becomes connected. Now we want to show that the graph has no cut vertex to prove that the graph is two connected. Now to show that, suppose you assume that there is a cut vertex V, and if there is a cut vertex V, then you know that suppose V is a cut vertex, then you know that there are two other vertices U and V such that for every UW path you are finding V in between them. But that contradicts that U and W has two internally disjoint paths. So if U and W have two internally disjoint paths between them, so it cannot happen that V is in between all the UW path, and so there is no cut vertex, and so you have the graph is two connected. Now the converse part says that if the graph is two connected, then we will show between any pair of distinct vertices two internally disjoint UV path. Now we prove by induction on the distance between U and V, and the basic step goes for the distance equal to 1. The distance equal to 1 means they are adjacent to each other, and suppose E is the edge between them, and then you have there is no cut vertex. So if you delete the edge E, that means the graph is not disconnected, because you know that if you delete U or V, the edge E is deleted, and so since U and V are not cut vertex, so deletion of this edge cannot make the graph disconnected, and so you have that G minus E is a connected graph. And if G minus E is a connected graph, then always you are getting a path between u and v which avoids e. And so these two paths, that u and v, they are already adjacent by the edge e, but we are saying that if we delete the edge e, the graph remains to be connected because the graph is too connected. So either if we remove u or if we remove v, which also deletes the edge e, but then the graph is not disconnected because u and v cannot be a cut vertex in a two connected graph. So deletion of the edge e cannot make the graph disconnected, and then that says that G minus E is a connected graph. Now if G minus E is a connected graph, naturally there is another path between U and V. If G minus E is connected, then there is another path between U and V which is not containing the edge E. So you see that this path UEV and this path another, these are internally disjoint paths between U and V. So this completes the basic step, and now we go for induction. As an inductive hypothesis, we assume that suppose the result is true for any 2 points or any 2 vertices of the graph whose distance is less than k. And now suppose we consider 2 vertices u and v whose distance is exactly equal to k, and then we will show 2 internally disjoint paths between them. So we will start by considering a length k uv path. So this is a uv path of length k. It starts from u, ends at v, and suppose that uk is the last vertex before v along the path. Now we will show it in a better diagrammatic way. So we see that we start with a path starting from u and ending with v, and that is a uv path in G of length k. We wish to show 2 internally disjoint paths between u and v. Now first we see that if we make the end of the path at uk, then since the distance between u and v along the path is of length k, so distance between u and uk along the path is k minus 1. So obviously the distance between u and uk is less than equal to k minus 1. Thus we get by induction hypothesis that u and uk have 2 internally disjoint paths, and these are suppose q1 and q2. So from u to uk, this is of length k minus 1. So by induction hypothesis, we get that there are 2 internally disjoint paths, q1 and q2. Now by using this q1 and q2 and some other path, we will construct the 2 internally disjoint paths between u and v. So let us see how we can construct this. Now we are making the argument that since G is 2 connected, uk cannot be a cut vertex. So uk is not a cut vertex since G is 2 connected, and so the graph G minus uk is still connected, and since the graph G minus uk is still connected, so in the graph G minus uk both u and v are present there. So you will get a path q3 between u and v in G minus uk, that is which avoids uk. You will get another path between u and v. But now this path may have the intersection with q1 and q2. So we assume that suppose w is the last vertex before v, which is common to q3 and with either q1 or q2. So w is the last vertex before v along q3, which is also common to either q1 or q2. So suppose for the time being we consider that the vertex w is common to q1, and then we are building 2 other paths q4 and q5 in such a way that from U to W we are moving along Q1, W to V we are moving along Q3. So we are moving along U to W through Q1 and then W to V along Q3, and this path we call that Q4. And another path we are constructing, that along Q2 we are moving U to UK and then we are considering the edge UKV. That path we are saying Q5. Now you can understand there is no common vertex in between Q4 and Q5 other than U and V. That is because Q1 and Q2 are two internally disjoint paths. So there are no common vertex between Q1 and Q2 other than U. And then for Q3 and Q2, you notice that since W was the last vertex in Q3 which appeared with the common of either Q1 and Q2, and here we are considering the case it is common with Q1. And so since Q1 and Q2 are internally disjoint, so W is now not belonging to Q2. So from W to V, this path along Q3, there is no common vertex between Q2 because W was the last common vertex that was possible to either Q1 or Q2. So after W, there is no common vertex between Q2 and Q3. So W to V along the path Q3 has no vertex common with Q2. And also since the path Q3 avoided UK, and therefore the vertex UK is also not belonging to Q3. So the only point common to this path of Q4 and Q5 is the first vertex U and the last vertex V. And so these are two internally disjoint paths between U and V. And similarly, we can prove that if W is a common vertex of Q2 and then that is the last vertex before V we can get common with Q3, then the proof is exactly same. You just consider that Q1 to be Q2 and Q2 to be Q1 in this diagram, and then you can easily understand that how we can construct two internally disjoint paths between U and V. So you see the proof is very beautiful, that is constructed over the induction of the distance between any two vertices of the graph, and we make the induction on the distance between two vertices on the graph, and we completed our basic step by considering that when the distance is 1, we have seen there is an edge between them, and then since the graph is two connected, if we delete the edge, the graph cannot be disconnected, because if we delete any endpoint, then also the graph is not disconnected, and deletion of any endpoint naturally makes the deletion of the edge, so the graph is not disconnected. So deletion of only the edge cannot make the graph disconnected. So you can always have a path between U and V other than using E, and so U, E, V and that path will be two internally disjoint paths. Now we go for induction, and we assume that any two vertices of distance less than k, the result is true. That is, if the graph is two connected, then there are two internally disjoint paths between them. Now we are considering two vertices U and V, and whose distance is k. So suppose there is a path between U and V of length k. So we now consider the path only from U to UK. Since this length is k minus 1, so the distance between U and UK is k minus less than equal to k minus 1. And so we use the induction hypothesis to get the two internally disjoint paths between U and UK. And now what we are doing, that we are noting that since again G is two connected, UK is not a cut vertex. So after deletion of UK, you can still have a path between U and V. And that we are using that suppose there is a path Q3 between U and V, but there might be some common between Q3 and Q1 and Q2. And suppose we consider that W is the last vertex before V. W is not V. W may be U, but W is not V. Then W is the last common vertex between Q3 and either of Q1 or Q2. And suppose in this diagram we consider that W is in Q1, and then we construct two internal disjoint paths between U and V in such a way, Q4 and Q5 in such a way that Q4 is constructed U to W along Q1 and then W to V along Q3, and Q5 is constructed U to UK along Q2 and then using the UK to V edge. And in this way we see that since there is no common vertices between Q1 and Q2, so U to W portion has no common vertex with this Q5, and then W was the last common vertex between Q3 and Q1 or Q2. So W is, we are considering W is in Q1, so W is not in Q2, and also W to Q3 has no common vertex with Q2, and finally UK is not belonging to Q3 by the construction because Q3 is constructed in G minus UK, and so there is no common part between Q5 and this part of Q3 W to V. So Q5 and Q4 are two internally disjoint paths, and that proves the theorem. The graph is two connected if and only if you have each pair of distinct vertices has two internally disjoint UV path. So in today's class we have several theorems and result that concerning the connectivity of a graph. We started with the result that a connected graph of n vertices has at least n minus 1 edges, and this is a necessary condition. And then we proved some sufficient condition that a simple graph of at most 2 n vertices is connected if degree of each vertex is at least n. Then we did some betterment of the result to prove that if there is a simple graph of n vertices and if the degree of each vertex is greater than equal to n minus 1 by 2, then also the graph is connected. And then we prove this result about the number of these vertices, edges and components, that if there are n vertices and k edges, then any graph has at least n minus k components. This was our third result. Then we developed the concept of connectivity and cut vertices, and we define the cut vertices of this kind of vertex that whose deletion makes the number of components higher, or you have that if the graph is disconnected, then it becomes disconnected. Then we get the result which characterizes cut vertices, that a vertex is a cut vertex in a connected graph if and only you have two different other vertices U and W such that that cut vertex is lying within every UW path. And after this result, then we prove that if there is a connected simple graph, then G has at least two vertices which are not cut vertices. So that is another result. And before that we have defined the vertex connectivity, and which says that this is the minimum number of vertices whose deletion from the graph makes the graph disconnected or leaves the graph with only one vertex. That is called the vertex connectivity of the graph, and that is denoted by kappa g, and if kappa g greater than equal to k, then we say the graph is k connected. Then we got this result that we mentioned here. Then similar to the vertex connectivity, we come to the concept of edge connectivity, and we define a cut edge or a bridge that if deletion of this edge makes the number of components higher, then we call it a cut edge. And there is a characterization of cut edge is that it is a cut edge if and only if it is belonging to a cycle. This result is also true for any graph. That is, the previous theorem was for connected graph only. Now for any graph, the result is true that a cut edge, an edge of a graph is a cut edge if and only if it does not belong to any cycle. Then we come to the concept of edge connectivity, and it is denoted by kappa dash g, and it is defined the minimum number of edges whose deletion leaves either a disconnected graph or a null graph. And then we have made a beautiful relation between the vertex connectivity, edge connectivity, and the minimum degree of the vertices delta G in this linear ordering, that kappa is less than equal to kappa dash less than equal to delta for any simple graph, where delta G is the minimum degree of the vertices of the graph. Now after this result, what is about the two connected graph? That if the graph is two connected, then we have seen that any two vertices are joined by two internally disjoint path, and the condition is also sufficient that if this happens, then the graph would be two connected. Next we consider a class of graphs that is called a bipartite graph. A graph is called bipartite if the whole vertex set is partitioned into two subsets such that in each subset no vertex is adjacent to the other. If the vertex set is V, then V is partitioned into two subsets V1 and V2, and which are disjoint, and the condition is that no two vertices of V1 are adjacent to each other and no two vertices of V2 are adjacent to each other. That is, the graphs are looking like this. Here are some examples of bipartite graphs. These bipartite graphs are complete bipartite graphs. We say that a bipartite graph is complete if every vertex of V1 is adjacent to every vertex of V2. Here in the first diagram you see that there are two vertices in V1 and three vertices are in V2, and V1 is adjacent to all of them 3 in V2 and V2 is adjacent to all of them 3 in V2. And similarly each vertex of V2, V3, V4, V5 all are adjacent to every vertex of V1, that is V1 and V2. So this graph we call a complete bipartite graph, and in its partition, in one partition there are two elements, in another partition there are three elements, and we denote this graph by K23. You can remember the complete graph of n vertices we denoted by Kn, and this complete graph of m and n vertices in the partite sets we denote it by Kmn. And symmetrically it is same as Knm. So K23 you can write it K32 also. Similarly you can see figures of K24 and K33. K33 is an important graph, and we will see its connection with the planarity when we learn the planar graphs. So these are all complete bipartite graphs, but in general the bipartite graphs may not be complete, and so may not be some edges are here. But in the bipartite graph, no two vertices in the same partite set, they are adjacent. So in general, a bipartite graph you can have this kind of figure, that suppose it is like this. And also bipartite graph may be disconnected also, that is in this way. So suppose there are two components of this bipartite graph, but one thing is easily understandable, that if each component is bipartite, then the whole graph becomes bipartite. You can have just collect this partition into one and collect this partition into the other. So in this way you can have, if different components are bipartite, then the whole graphs are bipartite. Now the first result, that if a bipartite graph is regular, that means each vertex has the same degree. Suppose the degree is k, then it is called a k-regular. So if the bipartite graph is a k-regular bipartite graph, and then the number of vertices in V1 is same as the number of vertices of V2. These are called equipartite bipartite graph. The proof is very simple. You can understand that every edge in the bipartite graph has one endpoint in one partite set and another endpoint in another partite set. So every edge adds 1 to the sum of degrees of the vertices of V1, and similarly every edge adds 1 to the sum of degrees of the vertices of V2. So each vertex has degree k. So there are k edges are incident to each vertex, and so the total number of edges in V1 is k times cardinality of V1, and similarly the total number of edges in V2 is the cardinality k times the cardinality of V2, and that is the total number of edges, as each edge contributes to the sum of degrees of vertices of V1 by 1, and each edge contributes to the sum of degrees of vertices of V2 by 1, and so each vertex has degree k. So the total number of edges incident to the vertices of V1 is k times cardinality of V1, and the same is for V2, k times the cardinality of V2, and which are both equal to the number of edges in the graph. And so immediately it follows that cardinality of V1 is equal to cardinality of V2. So every regular bipartite graphs are equipartite. This is the basically the result here. Now we go for the characterization of bipartite graph, and the characterization says that a graph is bipartite if and only if it does not contain any cycle of odd length. Here the statement is written for non-null graph, but any null graph you can make it bipartite, because if you have a null graph consisting of some vertices, and then you can make any subset of it as one partition, any subset of it is another partition. So every null graph is by default becomes bipartite graph. However, so what is most important is that every bipartite graph is not containing a cycle of odd length, and conversely what is more important is that if any graph does not contain any cycle of odd length, then the graph is bipartite. And this is the characterization of bipartite graph. Now to prove the result, first we prove a general result of graphs. You can remember we previously had a result that every closed walk contains a cycle. Now to be precise, here we want to prove that every closed odd walk contains an odd cycle. And we prove this by induction on the length of the walk, and suppose we consider it as L, the length of the walk, and basic step we complete with the case for N equal to 1, and for L equal to 1, so you can have only a loop here like this. You can have a loop, and every loop is a cycle, and so it is itself a cycle. So we consider that suppose it is true for any closed odd walk with the length less than L, and L is now greater than 1, and we are considering a closed odd walk of length L. Now if the closed odd walk itself is a cycle, that is there is no vertex repetition in it, then it is itself is a cycle and we have nothing to prove. So when the vertex repetition occurs, then you see when the vertex repetition occurs, then you see suppose in this figure this vertex V is repeated in this closed odd walk. This is the closed odd walk. You see that if you start from here, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and 17. So totally the length is 17, and it is a closed odd walk starting from this vertex and ending at this vertex. But here there are many vertices are repeating. This vertex is repeating, this vertex is repeating, this vertex is repeating. But suppose we consider the repetition of the vertex V here. In this tour of this closed odd walk, whenever we get a vertex repetition, you can understand from this vertex to that vertex again, that is when we are moving on, if there is a vertex repetition, then from that vertex to the repetition of the vertex again, so this part becomes another closed walk and the remaining part becomes another closed walk. So we have two parts of closed walk. So if this part is itself a cycle, then we have proved our result, so that the closed odd walk contains a cycle. But whether this part becomes a cycle or not, since both these part are closed odd walk, and so separately their length is less than the given closed odd walk, we get a closed odd walk in one part. Because the total is the odd, total number of length is odd. Suppose this part is L1 and this part is L2. You have that L1 plus L2 is odd, and so one of them must be odd. That is, one is even and another is odd, otherwise you cannot have the total is odd. Which part is odd? You just consider this part. Now length of this part is less than the length of the original closed odd walk, and so by induction hypothesis this part contains an odd cycle, and that proves that whole odd closed walk contains an odd cycle. So this is a simple thing that we have, but particularly interesting, and it will be used in the next theorem, that every closed odd walk contains an odd cycle, and we prove in this way that basic step we complete with the L equal to 1, that is the length of the walk is equal to 1, and then it is a loop, and so it is itself a cycle. Now if it is greater than 1, and we by induction hypothesis we consider that anything less than that is following the result, what we do, we consider that if there is no vertex repetition in the closed odd walk, then it is itself a cycle and we have nothing to prove. But if there is a vertex repetition, and then we just separate the portion of the repeating vertex one side and the other part other side, both of them forming the closed walk, but we consider that since the total length is odd, then sum of these two integer is odd, so one of them must be odd, and this odd part has the length less than the given closed odd walk, and it is another closed odd walk, but its length is less than the given one or less than L. So by induction hypothesis this part contains an odd cycle, and this odd cycle is obviously the part of the original walk, so every closed odd walk contains an odd cycle. Now using this result we will prove the characterizing theorem of the bipartite graphs, that, and you see that the result is done in 1936 by Koenig, that a graph is bipartite if and only it has no odd cycle. So it has two parts, if and only. So the necessary part says that if the graph is bipartite graph, then it has no odd cycle, and that is very clear. If we have a bipartite graph, and then you see that if we start with a vertex, then at the first step you go to the another partite set, and then if you want to return to the same partite set, then you need these two edges, and again if you move from this partite set, again if you want to return to the partite set, then you need another two edges. So in this way every return to the same partite set involve even number of edges. So since we are interested in our cycle, so this cycle can be formed where you have started and that the very vertex you are making an end. So you are returning to the same partite set, and it always involves the even number of edges. So no odd cycle can be formed here, only even cycle can be formed here. So it is clear that G has no odd cycle. So this is the necessary part. Now to prove the sufficient part, we see that now we will make the partition of the vertex set into two parts such that in each part no two vertices are adjacent to each other, and in this way we will show that the graph is bipartite. Now the proof is easy when the graph is connected, and so we consider that suppose the graph even if disconnected and it has several components. Now if we can prove that every component is bipartite, then we can prove the whole graph is bipartite as we explained before. So we consider that any component of the graph, and we will have that this part has no odd cycle, and we prove that this component is a bipartite graph. Now we fix a vertex u, and then we are calculating the distance of the vertex of any vertex from u, and this we are here denoting by f of v. F of v is here basically f of v is here the distance between u and v, that is the length of the shortest path between u and v, and we are considering this distance from fixing a vertex u, that for every vertex f of v is the length of the shortest path between u and v, and by default we are considering that f of u is 0, that is du u is 0. Now this distance can either be even or be odd. Now we are forming two sets x, the set of vertices where the distance from u is even, and the set of y, the set of vertices where the distance is odd. And we consider that du u is 0. Du u by default we consider that it is equal to 0, and so it u belongs to the set x. So in this way we can see that between these two sets there is no common element, because either the distance from u is even or the distance from u is odd, and also there is no escape from any vertex for being belonging to x and y, because if we calculate the distance, then the distance is either be even or be odd, so the vertex is either in x or in y. So in this way you see we have a clear partition of the vertex set into two parts, x and y, and where x and y are disjoint. So this partition is complete. The only thing we have to prove that no two vertices of x are adjacent to each other and no two vertices of y are adjacent to each other, and then our proof will be completed. Now you consider that suppose there are two vertices x1 and x2 of x, and now you take u, and suppose you consider there is an edge between them. Now there is a shortest path from u to x1 and there is another shortest path from u to x2. Since we are considering only one component, so the graph is now connected, so from every vertex to another there is a path, and so you have that u to x there is the path of even length, and u to x1 the path is of even length, u to x2 the path is of even length, and that with this edge x1 x2, so that form a closed odd walk. You see that if we start from u and go to the shortest path to x1, then traverse the edge x1 x2, and then back from x2 the path to u, and that forms a closed odd walk. There may be some common portion of these two paths from u to x1 and u to x2. So that is why we are saying that there is a closed odd walk, but just we have learned that whenever there is a closed odd walk, there is an odd cycle, and so the component contains an odd cycle, or the graph contains an odd cycle, and that is forbidden as our given condition that the graph has no odd cycle, and so it is not possible of having edges between any two vertices of x. Exactly in a similar way, we can show that it is not possible to having an edge of two vertices of y, that suppose y1 and y2 are two vertices of y, if they are connected by or they are joined by an edge, and then if we consider u, So similarly, you have a path from u to y1, a path from u to y2, and now these paths are of odd length, and this with the plus 1, odd plus 1 plus odd, totally it becomes an odd closed walk as before, and this odd closed walk contains an odd cycle. So in this case also we are getting a contradiction, as the graph contains no odd cycle, so there are no two vertices in y which are adjacent to each other, and therefore this forms a bipartition of the component, and the component becomes a bipartite graph, and just making together of all these components we get the whole graph becomes a bipartite graph. We see that the statement is that the graph is bipartite if and only if it has no odd cycle. So the necessary part goes in this way, that since the graph is bipartite, so there are no two vertices in the same partite sets which are adjacent to each other, and so if we make a cycle, then it has to return to the same partite set, and every time when it returns it involves even number of edges, and therefore there is no chance of having an odd cycle. On the other way, suppose we consider the graph has no odd cycle, and then we consider any component of the bipartite graph, and then we fix a vertex on that component, say u, and we calculate the distance from any other vertex from it, and we separate the two sets of vertices whose distance is even from u and whose distance is odd from u, and then we show that, and we trivially consider that the distance from u to u is 0, so it is belonging to x. Now, so since the component is connected, so for every vertex v there is a path from u to that vertex, and so either it belongs to x or it belongs to y, and so it becomes a partition of the vertex set, since there is no chance of any common vertex between them, because the distance either be even or be odd, cannot be both. So in this way, this makes the partition of the vertex set, and finally we show that no two vertices of x or no two vertices of y are adjacent to each other, and that we are showing in this way, that suppose there is an adjacent pair of vertices in x, and then u2 that x, suppose they are x1 and x2, so u2 x1 this is an even length of path, and then x1 x2 is plus 1, that is odd, and then x2 to u again are even length of path, so totally we get a closed odd walk, and we just proved that every closed odd walk contains an odd cycle, so we have an odd cycle here, but which is forbidden as to the given condition. Exactly in the similar way, we prove that no two vertices of y are adjacent to each other. So in this way, we show that each component is a bipartite graph, and the whole graph becomes bipartite. So this characterizes that a bipartite graph contains no odd cycle, and conversely. So we end this chapter with this result, and in this chapter we have learned many results of the connectedness of the graph and this characterization of bipartite graph. And before defining or studying the concept of connectedness, we defined various tours along the graph like walk, trail, path, cycle, circuit, etc. And with this result of bipartite graph, we make an end of this chapter.